Okay, so we're talking about web audio. Is anyone familiar with it already? Great. So it's a JavaScript API for audio manipulation. So you can play sounds, manipulate sounds. So that's what it is. So like previously, forever we had the embed tag. The kids use a MySpace and use Flash to play audio. In 2011, there was the audio tag with HTML5. I don't know exactly what the difference between that and the embed tag was. Maybe you could only play one sound at a time with the embed tag. Anyway, it sucked too. So now we have the web audio API, and it's just a lot better at everything. So it's a lot like the canvas tag for audio data. So the old audio tag was all like just an image tag. Like you could load up an image or audio thing from a remote source. You could play it back. You could like position it in time. You could also like synthesize with it in base64 data URLs, but that was horrible.
So when you say canvas for audio, do you still have the cores issue? Like if you load audio from a remote source?
I think you do, yeah.
Okay.
I think you can load in an audio tag. The audio tag lets you load in the audio data, and I think you load it in that way, you don't have the cores issue.
Yeah, because you can just play it, but if you try to modify it, then
right, but you can make an audio tag and not play it, but just route the sound into the web audio. So, yeah, I'm going to be doing like an AJAX request to load in data, but I think you can also do it through the audio tag, which should run into the cores issue. I'm not positive.
Thank you.
So it has audio stream read write, like I said. So you get control over the samples, like you can place data like at particular spots. You can timing control, where you can put it at like frame specific. You can put the audio where you want it. So like if you wanted to do a drum beat synthesizer, like you can get the timing exact. Like with the audio tag, you could say, I want to play this audio, and it would play as soon as it wanted to. But with this, you can say, play it exactly this time, and it will do it exactly then. You also get microphone access, which is unprecedented. And there's a really nice component library that goes with all this. So compatibility. This has been around since 2010 in Firefox as the web audio data API, I believe. But it's all been merged back into now web audio. It's supported almost everywhere for some time, except for IE, of course, because Edge also supports it. I don't know if anyone's familiar with that. I wasn't until I was researching this. But I think maybe it's the IE replacement for Microsoft. I'm not sure.
Basically,
Okay.
it was their rewrite, fresh start of their browser that came with Windows 10.
Is that going to be like going forward?
It sounds like it's their standard going forward, so they could dump their old rendering engine and all of the garbage that came with it.
Oh, great. So yeah, everybody's up to date, basically. So the simplest thing you can do with this is just to play a audio tone. So we're just going to create an oscillator node that generates just a sine wave, and we're going to hook it up to the destination, the speakers. Set the frequency. You can set the frequency to whatever you like, shape to whatever you like, sine waves, sawtooth. So I mean, this just sounds like. Is that volume good enough? Let's see. Sorry, guys. That's kind of loud. All right. Anyway. So everyone's familiar with like general audio graph. Like have like a magic school bus understanding of how these work. So yeah, you're just generating that sine wave. It's pretty straightforward. So this is the code. This is how you do it. The first concept here is this audio context. The audio context is like the root object for all of your audio processing needs. It stores things like where your speakers are and how to contact them, and it stores like your sample rate and your like the current time. So then we create an oscillator that context.create oscillator. That's what is generating our sine wave. And you can set the type and the frequency. You set them to arbitrary values. And you connect it up to your destination and start it. If you call start without any arguments, it'll start the audio right away. Stop, you can see we have a parameter on the time. And that says stop at current time plus 1 second. So it stops all by itself after a second. The oscilloscope.start is just a component that I made to show the how we can edit this. You can let's do a sawtooth wave. Everybody already knows the stuff that different types of waves sound different, right? So you have that. So another concept is, so we made this oscillator node and hooked it directly to the destination, but now we're going to put a gain node in between, and that acts as volume control. So the gain, like, it'll multiply those waves. Like if you set it to 2, it'll make them twice as high. If you set it to 0.5, it'll make them half as high. So we've hooked up the oscillator node to the gain node to the destination, and we're hooking up our range input to the gain. So with that range, we'll go from 0 to 1, and like you can see, so it gets quieter as you slide it down.
So your slider is the range input, right?
Yes.
Okay.
That's pretty simple too. So we're creating our context as before, our oscillator as before, setting the type and frequency the same. And the new thing is this gain node. And whenever the range input changes, we're setting the gain.value to the value of the range input. So just the position where it is on the slider. And then we call oscillator.connect to the gain, and gain.connect to the destination, and we start them up. So that does your volume control. Again, that's just. So everybody follow along so far? Okay. So next up, that gain parameter on gain node, those are kind of cool. On all of the audio nodes, most of the parameters are these audio params. And you can do more than just set the value to whatever you want. You can also do things like schedule them to go up and down at certain times, or you can even hook up other oscillators to them. So here we're picking up this automation schedule to the gain, and we're going to, we're going to have the same oscillator and the same gain, but instead of the range input, we're going to start the gain at 0, and it's going to go up really quick and then fade back down. So it'll sound like you're hitting a xylophone or something. So, and all you have to do there, so we're just creating our gain node and connecting it as before. And these 3 bits are the new thing. So we're saying linear ramped value at time. And we're sort of ramping up to 1 by the context, by the current time plus 0.2 seconds. And then we're ramping back down to near 0 at the current time plus 1.5 seconds. You can't actually go all the way to 0 with an exponential ramp, you just can't get there. So, yeah, everybody good so far? So you can also, instead of doing the automation schedule, you can hook up another oscillator to the gain. And so here we're going to have a slow oscillator that modulates the gain. And so that'll go. That's pretty simple too. You just have, we're creating our oscillator before, and we're creating this other low frequency oscillator. And we're connecting the LFO to the gain's gain. That's the gain's audio parameter called gain that controls the actual gain of the gain node. And then we're starting up as before, and that's that. You can also modulate other parameters. So like as I said, basically every parameter is audio parameters. So we're doing the same thing with that low frequency oscillator, but instead of modulating the volume, we're going to modulate the frequency of our primary oscillator. So what this chain is going to do is going to modulate the frequency from 420 to 460. So that's what you see that gain node in the middle? If you didn't have that, it would only modulate between 439 to 441. So that gain node steps up the low frequency oscillator from just going from 0 to 1 to 0 to negative 1 to 0 to 1, up to going to 20 to negative 20 to 20 to negative 20. So that's why that's there. And again, pretty simple. We have our low frequency oscillator. The only difference in this code right here is that we're connecting the LFO to the gain and the gain to the frequency instead of like we're swapping on the order of the connections. This is the same as the previous example, except for the connections are swapped around. Good. So another popular thing is playing back an audio piece from a file, from a web. So what I'm doing is just I'm going to make an XML request to a file on my server, and I'm going to send the response to the context decode audio data function, and that gives us a buffer that we can use for this buffer source. We can type the buffer source to the destination. So does that make sense to you? The buffer source is a new thing. It plays a audio buffer. So I mean the buffer is like the actual value of the. It's an array with values that represent what we want it to do, and the buffer source just plays that buffer.
It's essentially binary wave audio data.
Yeah. So let me just. So that's really easy to do. You just set up that request and you send it. You can see the context here. We're creating. So let's take a look at it. But there's that context code audio data. It takes a callback, and the callback returns the buffer.
So if you were going to put this on a real web page, say like in a game or something like that, and you wanted to do this repeatedly, you'd probably, I'm assuming you'd probably load the file asynchronously up front and store the, load it, decode it, and then store the buffer in a variable so that you did on-demand playback immediately.
Yeah. Yeah. So you load up all your audio sources, and then you'd have the buffers loaded somewhere cached. You're creating this buffer. Each time you want to play the audio, you create a new buffer source. Those are just cheap. The expensive part is that audio data that you send to the buffer. You can only play a buffer source once. So that's an interesting fact.
The buffer that you're sending into that is the parameters and callback and decode audio data.
Right. Yep, so also you can play back, as I mentioned, we can do exact timing. So for the rest of the example, I'm going to use this load buffer function, and it just loads it up and gives us a callback that we can use trivially. It's not important, it's basically the same as the last example, except promises are fun. So we're going to load the buffer, we're going to load this buffer from the web, and then with that buffer, we are going to explain this anonymous function. Anyway, so we're going to request that it be played at, so this is another interesting point. See, when you, we're doing source.start at a time, and you want that time to be in the future a little bit. If it's in the past, it'll play it immediately, and you don't get your exact timing. So you want to tell it to play it soon, but not in the past. So we have that start equals the current time plus 100 milliseconds, and we're saying play it at the start plus 0 and the start plus 7 quarter interval and 90. That lets us get like frame perfect audio placement.
Why do you have the interval exactly? Is that the length of the audio file?
No, the interval is just like it's the pace. So like if we set that to 0.25, then it would go more like, so it's just, sorry, pacing. Gotcha. User interaction-based timing basically is the same thing, but I was going to show that you can like play it in sync with the beat of another music file. So like we can play some music, and then you can get so I think that's cool. So like you make like a space shooter and have like the background music and have it like audio sync. I think that'd be really cool. I didn't make that. Not really going to go over the code for it, but it's not that hard. And
200 lines.
Yeah. All these slides are available on the web right now if you want to follow along. I'm not going to tell you where.
Oh.
So the other thing that the cool thing you can do is that you can capture the microphone data. This with some new APIs, you can get the user media, and you can create this media stream source. It's just another source like that oscillator source or the buffer source. And you hook up, you ask for the user media with audio true, video false, and it just gives you the audio stream. And you can hook that up to the stream of the media source. I put in a delay node so that we can hear it. Otherwise, it would just sound like I'm being amplified. So let it use the microphone, and so you can see like yeah, that's it. So this is a lot like yeah. So we just use the navigator to get user media, and there's the callback. You create your context again, and create media stream source with the stream that you got from the user media callback, and then you just hook it up like normal. That delay is new too, I guess. The delay node delays the audio. It's pretty simple. So,
is that oscilloscope part of the API as well, or is that something else?
No, that's fine. Yeah, I can show you that.
That alone is really cool, along with the rest of it. The fact that you have a visualizer to go with it.
Yeah. The oscilloscope is pretty simple, but it's scattered in the source of this page, so it's hard to get to. I mean, it's just, there's an analyzer node that I'll show you later that you can connect to, and it gives you the streams. I'm just plotting that on a canvas every 20 milliseconds. So also there's a playback rate on the buffer source. That's what we use for music. And you can use that to slow down or speed up the audio. So, I mean, all these are the same, really. Like, if you understand the diagram it's hooked up, you don't need to see the code. If you want to, you can look at it later. But, yes?
I noticed that one looked like you're playing MP3, correct?
Yeah, I think it was an MP3, right?
So it doesn't have, because I know some audio libraries have issues with different encodings.
Yeah.
So this one's pretty flexible then?
Yes, I don't. It depends on the browser what all it will support. I can't tell you exactly.
Oh, okay.
But Chrome is pretty good at playing anything.
Cool. So this one, but one of the things that was different from earlier is you mentioned that you need the decode node in there. It does not need to decode MP3.
No, there's still the decode. This load buffer function.
Am I missing it somewhere?
This load buffer function handles all of that. We
put
created
all
that
together.
earlier, like here. So that handles the decode audio data. Like,
Okay.
takes the parameter of the context and the URL. So that's how that's handled.
Forgot about that part.
So we covered playback rate. So when we did this, like you can see, like there was. If you want to do pitch shifting, you'll also get the audio playback rate change. Like the playback rate and the pitch are linked. So if you want to unlink the pitch and the playback rate, this is really complicated and I'm not going to go over it well. The idea is you'll play, this is just one of many pitch shifting algorithms, but in this one you play back slowly, but you only play back a section of it and then you jump and you play. So like you play very small sections of it slowly, and you do it over 2 channels and you fade them in and out. And I don't know.
It works?
Yeah, it works. And it doesn't work well because I didn't really my game fixed up correctly. So you can do it. It's not the most interesting anyways. There's a frequency filter, so you can filter out like the lower or higher frequency components. That's this biquad filter, and so you can like do a low pass filter and muffle it, or like make it sound like it's over the telephone. Doesn't really change a whole lot. Or like it's on a pair of headphones on your desk. Like it's very high So yeah, you can use that for like room effects. Like if you're like playing a game and you're like moving outside of the room where the audio is, you can drop that low pass filter.
This is like not
All right, I just hit that run button twice, which was a mistake.
oh, but we liked it.
Please. Okay. So yeah, I mean, that filter node, there's different types. Like you can do a low pass that makes that muffle sound. You can set the frequency to whatever you like. That telephone is a band pass that represents the telephone audio frequency range. It's high to 300, low to 3. You can see. So it attenuates all the frequencies outside of that. Headphones is a high pass filter that I've set to like only play sounds that are above 8,000 hertz. So using all that, we can make like a cool Doppler effect. So I just have a truck rumbling sound, and you can have the automation schedule on the playback rate to make it go, you know, like the first thing with Doppler is like it'll be low to start with, and as it goes past, it'll be high as it's coming towards you, and then lower as it's going away. So you can change the playback rate to reflect that. You can use a pan node that switches the audio from one source to the other. So at negative 0.5, it'll be on like the left side, and at positive 0.5, it'll be on the right side. Actually, at negative 1, it'll be all the way on the left, and at positive 1 will be all the way on the right. There's that gain node, which, because as it gets closer, it's going to be louder, and then as it goes away, it's going to be softer again. Another thing you might think of is the bipod filter. When things are further away, the high frequencies get attenuated. So as it gets closer, you'll be able to hear like the higher pitch of the higher frequencies of the engine rumbling. So that's just like and that's just a static file of an engine rumbling that I don't have a good way to play by itself. I mean, all this is just like wiring up the different filters and things, so it's not. I'm just doing this to play the music source by itself. I wish I weren't doing any of this. I'm not going to show you what the source sound sounded like, but you can just trust me that it was a single. Oh no, what's happened? Please come back. Right. Yeah, you can just it's just a single rumbling engine sound, and you can chain all these filters together and make something cool. So there's that. So another set of filters is like a convolution filter. So these are kind of complicated. What you're doing, you have an input signal, like your oscillator, and you have a convolution signal, which is so it's a way of mixing two signals together. So what we're doing, so the output is this summed column. As we go along, so how should I explain this better? It's really cool visualization though. So you're multiplying piecewise the input with this. This is just a reversed copy of this signal, and you're shifting it along the input and multiplying it piecewise. So it's 0 along until you get. Is anyone following this at all? Has anyone played with convolution before, or like taken like a signal processing anything? But you can see as so like this is just like a rolling average on the input signal. So it's just taking the like that width of.
I think I kind of get what you're saying. So it's everything, the convolver is saying take everything from in this chunk of time and make an average of it, and then let's roll along there and we'll multiply the input signal by that average. And I can see kind of how it ends up deforming it, because in between the first and second humps, there's supposed to be more of a valley, but it gets averaged out in the summed version at the bottom.
Right. Yeah. So like this signal, it's just going to be 3 spikes, and so the first spike is going to come along, and it's going to print out the input signal. And we have another spike that will be sliding along, and it will print it out at a lower value because the spike is lower, and then the third spike. I am running low on time. So you can see like with these 3 spikes, it prints out the signal 3 times lower. So that's what we're going to actually show you here. I have a convolver node, and I have, so those spikes are this 1/2, a quarter, and we just put this array into the convolver node, and we'll do So the other thing is there's impulse response assets. People will like record like a clap in a room, and how it echoes around the room, like will record that clap, and they can convolve it with your input signal, and it'll sound like that signal is played in that room.
Real quick question. With the one that you just did, with that exact convolver, is that the same? Is that if you go out to like a canyon, if you get an echo, is that what that basically is? Because you hear it at full, like a higher, larger volume, and each one you hear a little less.
Yeah. It's kind of like. Yeah. I mean, it was just an echo, like.
Yeah. Like echo.
Yeah.
Okay.
Yeah, it's like we can load up these assets. So, like, this is a pulse that was recorded in this factory hall. And if you play that against the music, and then he had a PA horn that was set up in that same hall, and it sounded like that. And you can play it. So, yeah, you can get these different impulse response assets, and like here's one that sounds like it's from a telephone.
You're like the gospel church. Yeah.
I have a glass cup. Inside a washing machine. I don't know.
That's awesome.
So, final thing you can do, not quite final, but so you can do like pitch detection. That's what this autocorrelation helps you do. So we have an input signal, and we want to know like how quickly it's repeating itself. That way we can figure out like what note you're trying to whistle or sing. So we have this autocorrelation technique. And what we're doing here is we're taking this input signal and subtracting this shifted signal. So it's the same signal, and we're subtracting it from itself. The correlated version, like that's an exact match, so it's all zero because it's the same signal. It's not been shifted at all. But as you move it, there's a difference between the peaks. Like, let's get over to like here. So see this peak right here. That's because this one is pretty low and this is pretty high. So there's a peak in the correlated signal. You're just subtracting them and taking the absolute value. So then, as you run it along, you'll find a spot where it matches up again. And then it goes away. And if you find that, in the first peak is here, but if you find that second peak, that's a good indicator of what frequency is being played. So what I'm doing, I have you want to use this so far? So taking my audio source, and I'm creating this analyzer node. This node that this helps you make visualizations. I'm using it for my oscilloscopes as well. And you can grab there's a method on it called get time domain float data, and that will give you the waveform that you're currently playing. And then we auto-correlate that, and we find the peaks of it, and we grab the second peak. So, like, I'm recording from the microphone now, and like you can. So there's your waveform from that hum, and you autocorrelate it to itself. So you shift it along, it finds out that it's a perfect match, or a close to perfect match, at that second peak. And that 140 is off. I don't know why it decided to stay at 140. yeah, so that's how you do that. So just different sounds, like different, wait. That was pretty accurate. All right, anyway, next up is, another thing you do with the analyzer node is get the frequency data. That does it through this Fourier transform type thing, where it's really the same kind of autocorrelation, or the same kind of correlation, but with a sine wave on the signal. And so this input signal is made up of one low frequency sine wave, and then a higher frequency sine wave, and then a really high one that's doing the zigzags. So as we use this to compare. So when we hit rate, what, like right there? Yeah. See how that sine wave is, it matches the first major wave. You multiply them together, and there's this peak in the. Oh, so the sum graph. Actually, so you multiply it piecewise, and then you add up the entire line. So you like sum all of the values along that multiplied line, and that's what the sum line is. That's your output. And that's not quite a Fourier transform. That's more like a discrete sine transform. You also, to do a full Fourier transform, you would also do a cosine, which is just a shifted sign. But you can see it finds that peak, and then a little bit further, it finds that second peak, and then once it gets to match the final peak, there it goes. See, it matches that final zigzag. Also, you can do it with pen signals. See what there's just different frequency components that it's finding in that sawtooth wave. So with that, we can create a spectrogram. And what that's doing is the values, like I'm going to take this sum line, and I'm going to flip it up vertically, and the peak is going to be like how white I'm going to draw it. And so you can see, like, as I'm talking, it creates those are all the frequency components of my voice. Like, you can.
That's cool.
So you can see, like, if you whistle. You can tell, like, different frictives, like. And they have different frequency components for each of the. So that's really cool too. And you can also use that for pitch detection. The autocorrelation is a little bit better because you often have like a noisy signal, and it's hard to find the exact right spot on the Fourier transform. Like if you whistle, you can get. But if you have like an airy, noisy whistle, like, that's not pretty good. But so, yeah, this corresponds to frequency components. And that's all I've got. That's the end of my presentation. Why is there one down? That's just the code. That's not terribly interesting either. It's just how it's all put together.
It'll be interesting for us to read later.
Yeah. The spectrogram is really pretty simple. It's just like on every tick, we're calling this get byte frequency data. The get byte frequency data is the the byte frequency data, and we're plotting it on our cumulative plot, and that's all there is to it. So, yeah. Any like questions or anything?
Sure. Do they have libraries for this where they've already used these tools to simulate different musical instruments?
Probably. I know there's different effects libraries that I've seen, like someone implemented that pitch shift bending algorithm way better than I did. So yeah, there's different libraries that go with this.
So, are you using, this was cool, what are you using it for? Like, what got you going?
So in the spring, I wanted to synthesize like a door stopper springing.
Like, is it pretty?
The twang noise, the twang.
Yeah.
Yeah, the thing's awesome.
Yeah.
So did you do it?
I did. I don't know. I don't know. Can I have access to it?
Maybe you could add it to the.
Is this it? I don't know. That was about as good as I got.
It's cool, I can do
I
this.
tried.
Awesome. Cool.
Cool.